All right, students, continuing on with my examples. Let's see, the second one on my list, I believe, was 14. Yeah, so we did 4. Let's jump over to 14. I decided to print it. I didn't have to carry the whole big book under the camera here. But let's read it here. Here it says a power plant operates with a 32% efficiency during the summer when seawater is used to cool it at 20 degrees Celsius. The plant uses 350 degrees steam and it drives the turbines. All right, so I guess it works something like this, that, here is the turbines or the engine, and it's got this steam under a temperature of 350 degrees Celsius. And so this is where the hot pressurized gas, which is H2O, expands and pushes a turbine, sort of like a windmill-looking device here. And then, of course, it turns the turbines, and the phrase we like to use is moving magnets make electricity. There would be some coils that would be spinning near a magnet, or a magnet that would be spinning near a coil, and it would do the work. And this would make our electricity. I think that's what they mean here by a power plant operates at 32% efficient. So I'll call that about 1/3. So about 1/3 of the thermal energy that goes in here and then comes out as work. So then the 2/3 come out as just hot steam or hot water here. If the plant efficiency changes in the same proportion as the ideal efficiency when the plant efficiency is in the winter, so they're going to then say that it goes up in efficiency because we have a colder temperature. And so maybe this is a good time to mention a little bit, again, maybe more about the entropy, but there would be some entropy coming in, and because of the entropy, we got to get the entropy out. And since entropy, a little change in entropy, is a little bit of energy at that given temperature, you can pack in more entropy, if you will, at a lower temperature. And therefore, we can get the same amount of entropy out of our engine as we put in. That way we can get the engine back where it started. And so there is no gain in entropy of the engine. It's not building up, and it actually is repeatable. You can go back to where you started. So the whole turbine keeps repeating itself. But to do that, we've got to take as much entropy out as we put in. And at the lower temperature, we can concentrate that entropy and get it out. So we can actually use less energy to get the same entropy out. Therefore, there's a difference, and that would be available to do the work. And so that's why we refer to the entropy as a measurement of the energy that, doesn't have the ability to do any work with. We need a certain amount of energy to store our entropy. And that's at least that's the macroscopic view. The microscopic view is that it's the most probable state. And so we just know that, this thing's going to manipulate around, and when it comes out, it's got to be in a more probable state as we mix things around, and that's the statistical nature of it. All right. So that being said, let me come back up here because I kind of got off track. This problem has nothing to do with entropy at all. It is just talking about the efficiency. And so let me put an E and another E. I'll put a little sub-E for the ideal Carnot cycle, and maybe I'll put a little R here for our real engine here. Okay, because they're saying that our real engine operates at a 32% efficiency. So let me write it as a 0.320. That's our real efficiency. The plant operates at 30, blah, 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 but then they go on. Now, if we were to ask this question about, okay, what is the ideal efficiency? That was the whole Carnot cycle issue. And so we could come up here and say, all right, so the Carnot cycle would be operating at 1 minus, and let's see, during the summer, with 273 plus 20 is 293. And maybe I'll just double check here, or make sure I do this one with my calculator with a 273, and then the warmer temperature is 350. So that is a 623. So if I go 1 minus 293 divided by 623, we're saying that this could be, excuse me, 53.0% if it operated in a Carnot cycle. And so remember that whole idea that, well, we can't really operate anything practical on a Carnot cycle. It has to operate at an infinitely slow amount of transfer time. So it takes an infinite amount of time to do one cycle. So we just kind of give us an idea of what we would shoot for. And so something operating like this, you might say, hey, I don't ever expect to get 100% efficiency, but I do expect to get better than 32%. So we could probably add some design features to this and ask, is it cost effective to increase the efficiency? Because it's probably going to be a huge cost to get us up to maybe 35% or 40%, but at least we have a room to shoot for. And we know we should be shooting for 53%. And so we're quite a ways from 53%. So I would think there'd be some cost-effective alternative. Usually these turbines are actually built in multiple stages. You expand the steam a little bit and they cool, then you have a second layer and then a third layer. And that's how you start to get efficiencies close to the ideal Carnot efficiency than in your steam power plants that way even. And so we do better and better and take advantage of what we call the waste heat. After the first expansion, you don't just get rid of it. You say, well, it's still warm, depending on how much you've expanded. Yeah. Anyways, that being said, then it says here, if the plant's efficiency changes in the same proportions as an ideal one. So let's then ask this question. If we were operating at a different range of temperatures, so in other words, we cooled it down to 283 because we're using the seawater of winter time. We're still kind of boiling our steam to the same high temperature. It looks like they got us at 350 degrees Celsius. For whatever reason, maybe that's kind of a limit due to the strength of our materials. We know that, if we start to get above that temperature, our materials get weak, and if they get too weak, obviously we have steam under high pressures. And this doesn't say how much the high pressure is, but I can imagine that the pressure would be quite high, and as a result of that, you wouldn't want your containment, your metal, to get too weak. So anyways, so we'll leave the upper limit the same here and say, all right, in a winter time, maybe we could shoot for a little higher efficiency. Not too much better, but it does get better. It gets to 0.54, and I'm going to do another digit here, 6. So there was an increase, a small percentage increase, but what it's saying here is perhaps the real engine would have the same increase. So if the plant's engine changes in the same proportion as the ideal efficiency. So, maybe I would say something like this. The efficiency of the Carnot cycle in winter compared to the efficiency of the Carnot cycle in summer would have the same proportion, the same increase as the efficiency of the real engine in winter compared to the efficiency of the real engine in summer. And so in winter, for the Carnot cycle, we got the 0.546, and in the summer, we got the 0.530. Now, this is what we're looking for, is what is the efficiency of the real engine in winter, knowing that in the summertime, they got this 0.32. 2. And so now, grabbing my calculator, I can take this 0.546 here and divide it by 0.530 and then multiply it by 0.32. Oops, syntax. Oh, bummer, I did a double divide here. All right, let's see if that helps. Okay, so it looks like it's going to boost it up to, about 33%. And so we get it 1 more percentage better. But remember, it's 1 part out of a third. So, 0.01 out of 0.023 is a 3% increase in efficiency. So we get 3% more electricity just because the season changed and the water temperature cooling changed. Perhaps, because we don't really know how the operation of the real power plant works. We don't know if changing the seawater really has an effect on it. But probably does, because we're using that as the cooling side. But more importantly, it gave us something to talk about. And this is what I wanted to do, was to point out the efficiency of the Carnot cycle, the ideal one and the real ones, and how they're not quite the same. All right. Hope that was a little helpful. Take care.